Recall that we can prove that 0.9 repeating is equal to 1, and that we can do this with the use of infinitesimals to assist in our intuition. The idea of using a limiting value, or limits, are another method of answering questions about forever and forever close. However, unlike the use of infinitesimals, this method allows us to work solely from within the model of the real numbers. In front of you, you see another example of this, where we asked you, what was the proportion of this shape? How much of it was the dark side? How much of it was the lighter gray side? And this is a difficult question, but after a little bit of play, you might recognize that this is a shape that appears to be symmetric across a diagonal. And we could use reasoning to determine that if it's symmetric across the diagonal, then each of the shapes must be equal to half of the total area. Now, we did say that the way that we constructed this shape, if you'll recall back from task 1, was by dividing up the entire square into thirds, and then giving 1/3 to the dark side, 1/3 to the lighter gray side, and then repeating this process over and over again. So we've already seen the idea of limiting values. Here, we're just simply looking at them in a more formal context. So first, let's write a formal definition for a limiting value. The definition we'll use is more of a prescription rather than a recognition of existence, because as we'll discover later, not all expressions possess a limiting value. Instead, we'll just say something to the effect of, if it exists, then it must behave like, and then we'll continue through with our logic. So this is a common technique that we'll be using to define abstract concepts all through calculus. If it exists, then it must have the properties. Here, we see the definition for limiting value. An expression will be said to have a limiting value if there is a number closest to the result of the expression. So, for certain expressions, the limiting value is simply going to be the expression itself. For example, if I asked you what's the limiting value of the expression 2 plus 3, we'd say the limiting value is simply 5, since 5 is the number closest to the result of that expression. Now, let us see how we might use the logic of limiting values to solve a distance paradox or a parallel problem like the 0.9 repeating. If you interpret the 0.9 bar notation or the 0.9 repeating to mean find the limiting value of the expression 9/10 plus 9/100 plus 9,000, etc., then the number 1 fits the definition of limiting value. Therefore, 0.9 repeating is equal to 1. We can see this is a lot easier of a proof than it was using infinitesimals. With the help of limiting values, we're now able to address a number of different concepts, in fact, all with the same versatile tool, all while remaining in the realm of the real numbers. So for example, let's consider the irrational numbers, like the square root of 2, which we know to be calculated at 1.41423, etc. We can now think of this number not as a standalone value, but as the limiting value for the expression of adding up each of the places. So we can think of this as 1 plus 4/10 plus 1/100 plus 4,000 plus 2/10,000, etc. And in such a way, we're able to talk about these difficult irrational numbers as just being the end result of following what we know the square root of 2's limiting value to be. Another example is we could just look at the area of the circle as being the limiting value of the area that we get from approximating the circle with polygons. We can also think about that paradox we know back from Zeno that we were looking at, and that is if we're in a corridor and we're trying to go half of the distance and then a half of that half, and etc., what is it that we would actually need to do to reach the end of the corridor? Well, here we can just simply look at adding 1/2 and 1/4 and 1/8 and say that the limiting value of doing something forever gets us to that destination of 1. Now, as we mentioned, limiting values do not always have to exist. So consider here that if we have an expression like 1 plus 2 plus 3 plus etc., this does not have to have a limiting value because there is going to be no number in the real number line that's going to be closest to the result here. This is going to continue to grow up to the boundary of infinity, and thus there is no real limit. Also notice that there isn't a limiting value for an expression like this sequence or pattern of sine 0 and then sine pi over 2 and then sine pi, because if we look at this pattern, what we have is an alternation that's going from 0 to 1 to 0 to -1 and around that unit circle, around and around and around. There is not one value that is closest to the result of this expression, so we're not going to say that this has a limiting value. We'll often choose to model problems either with the use of the infinitesimals or the limiting values, depending on which provides a more intuitive method for us. However, at their core, they share the exact same logical structure. Infinite values can be related to limiting values of infinite growth, whereas infinitesimal values can be related to this idea of infinite decay or approaching forever close.